Hello everyone, welcome to this lecture. So, in this lecture we will discuss what are the challenges we face when we try to run the BGW protocol for evaluating the nonlinear gates in the circuit, namely the multiplication gates. So, before that let us quickly go through the summary of the linearity property of Samir secret sharing. So, we had seen earlier that Samir secret sharing has this very nice linearity property that if you have secret shared inputs, then you can compute any publicly known linear function of their of those secret shared inputs without requiring any interaction among the parties. So, for instance, if you have two secrets say S and S prime which are secret shared through an instance of NT Samir secret sharing, and if you want the parties to have their shares for S plus S prime, then it is enough if each party individually adds its shares of S and S prime. That will give that party its share of S plus S prime. Okay. In the same way, if there is some publicly known constant say C, and if there is a value, if there is a secret S which is secret shared, then to get a secret sharing of S plus C, it is enough if each party adds this constant C to its own share of S. And in the same way, to get a secret sharing of S times C, it is enough if each party locally multiplies its share of S with this publicly known constant C. However, if there are two secrets S and S prime which are secret shared as per the Samir secret sharing scheme with degree of sharing being T, and now if each party locally multiplies its individual shares of S and S prime, then the resultant vector of shares will lie on a 2t degree polynomial whose constant term will be S times S prime. So, this polynomial A times B is a 2t degree polynomial, and its constant term will be the product of the constant term of the A polynomial and B polynomial, which is S times S prime. So, even though this vector of shares constitute a Samir secret sharing of S times S prime, the problem here is that now the degree of the sharing is 2t, it is no longer t, and that is one of the major problems which we face when we try to maintain the BGW invariant in the BGW protocol while evaluating the multiplication gates. So, now we will discuss the challenges which we face when we try to maintain the BGW invariant for multiplication gates. So, for simplicity, consider that we have a simple function consisting of just a single multiplication gate in the circuit. So, you have two inputs x1 and x2 held by P1, P2, P3 and P4 have no inputs here. So, you can imagine that their inputs are some public constant say 1, okay. And the circuit output is the product of the inputs of the product of the inputs of party 1 and party 2. And for the purpose of demonstration here, I am assuming t is equal to 1, that means any one out of these 4 parties can be corrupt. Now, we want the BGW protocol should help us to achieve the following property. We want at the end of the protocol everyone should learn the product of x1 and x2, and no additional information should be learnt beyond what can be learnt from the output y and the inputs of the corrupt parties. So, what will be the BGW protocol in this context? Say every party verifiably secret shares its input using the polynomial based verifiable secret sharing scheme. So, in this case P1 will act as a dealer and invoke an instance of VSS to secret share its input x1. Similarly, P2 will act as a dealer to verifiably secret share its input x2. P3 and P4 does not have any inputs here. Okay. So, the shares of x1 are denoted by x11, x12, x13, x14, and each share, one of the shares among these 4 shares will be available with one of the parties, and so on. Now, let us assume, let us suppose here that the parties try to go and evaluate this multiplication gate by simply multiplying their shares of x 1 and x 2. Okay. That is what the parties would have done if this would have been an addition gate. So, we are proposing the same step even for a multiplication gate. So, the proposed protocol here is that if you have a multiplication gate in the circuit, let the parties multiply their respective shares of x 1 and x 2. So, P 1 multiplies its shares of x 1 and x 2 to get the share y 1, and in the similarly P 2 multiplies its share of x 1 and x 2 to get its share of y. P 3 multiplies its shares of x 1 and x 2 to get its share of y, and P 4 multiplies its share of x 1 and x 2 to get its share of y. So, as I said earlier that this vector of shares y 1, y 2, y 3, y 4 they lie on a 2t degree polynomial now whose constant term is y. And now, since there are no more gates in the circuit, so this is the function f which we want to compute, right. So, as per the BGW protocol, the parties make public their shares of y, and to error correct the potentially corrupt shares which can be made public by corrupt parties, we apply the Reed-Solomon error correction algorithm and hope that we get back the function output y. That is a proposed protocol. Now, there are 2 problems with our protocol, and let us discuss both the problems individually. So, the first problem with the proposed protocol is that if we are in a setting where t is less than n over 3, and which will be the case looking ahead for the BGW protocol, and which also happens to be the optimal resilience for perfectly secure MPC, then this function output y need not be reconstructed back correctly if t shareholders produce incorrect shares of y. This is because now the degree of the underlying sharing polynomial is 2t. Specifically, we need the condition n greater than 4t to hold to error correct t errors and reconstruct back a 2t degree sharing polynomial, right. So, recall that the shares y 1, y 2, y 3, y 4 they now lie on a 2t degree polynomial, and up to t shares among y 1, y 2, y 3 up to y n can be corrupt. Okay. So, for the purpose of demonstration we have taken t equal to 1, that means 1 out of these 4 shares can be corrupt. Which share is corrupt we do not know, because we do not know the identity of the corrupt party. So, with the help of 4 shares among which one is corrupt and such that the shares lying on a 2 degree polynomial, we will not be able to recover back the value y. Okay. Because the coding theory bound says that the number of shares minus degree of the polynomial plus 1 should be greater than equal to 2 times the number of errors which we want to correct, error correct. So, in this case the number of shares is n, okay, and the degree of the polynomial happens to be now 2t, because these shares y 1, y 2, y 3, y 4 they constitute distinct points on a 2t degree polynomial. Okay. So, we need this condition to hold, that means n should be greater than equal to 4t plus 1, but that need not be the case, because we would like to design the BGW protocol, and looking ahead we will see that the actual BGW protocol is with only t less than n over 3. So, if we are in the setting where t is less than n over 3 and if we want to reconstruct a 2t degree polynomial using the help of n shares of which up to t are corrupt, we will not be able to do that. And as a result, the parties may end up reconstructing an incorrect function output. So, let me demonstrate this problem with an example where I take this as my field Z5 and my evaluation points associated with the 4 parties are 1, 2, 3 and 4. So, imagine x 1 is equal to 0 and x 2 is equal to 1 and say x 1 is VSS shared through this 1 degree polynomial, resulting in the shares 1, 2, 3 and 4 for the parties P 1, P 2, P 3 and P 4 respectively. Remember that all the plus and all the multiplication operations are performed modulo 5 here. In the same way, suppose the value x 2 is equal to 1 is VSS shared through this 1 degree polynomial. This will result in the shares 0, 4, 3 and 2 for the first, second, third and fourth party respectively. And now, since one of the 4 parties can be corrupt, imagine that it is the 4th party. Okay. Of course, this is just for the demonstration purpose. Parties will not be knowing who exactly is the corrupt party, except that one among the 4 parties is corrupt. So, as per the proposed protocol, every party should locally multiply its shares of x 1 and x 2 and make that share public. So, P 1 will make public the share 0, P 2 is honest, it will make public the share 3, P 3 is also honest, it will make public the share 4, but P 4 ideally should make public the share 3, because the product of its shares of x 1 and x 2 is 8, 8 modulo 5 is 3, but since P 4 is corrupt, it is making an incorrect share, say the value 4 as public. Now, everyone knows that among these 4 shares, one of the shares is corrupt and these shares lie on a 2 degree polynomial. Now, if the parties ignore the share of the 4th party, okay, and interpolate the shares of the first, second and third party, then they will reconstruct a 2 degree polynomial 4 z square plus z whose constant term is 0, resulting in the function output y is equal to 0. And actually this is the right output, this is the supposed polynomial, this polynomial 4 z square plus z is the supposed polynomial which the parties should reconstruct if they have the knowledge that party 4 is the corrupt party. So, if the parties would have this prior knowledge that it is the 4th party who is corrupt, then they could have simply ignored the share of the last party, the 4th party, and by interpolating the remaining 3 shares they would have recovered the right polynomial and the right output. But in this case the parties have absolutely no idea who exactly is the corrupt entity among the 4 entities. So, this is just one heuristic. It could be also possible that parties make the heuristic that it is the first party who is corrupt. So, ignore the share of the first party and use the remaining 3 shares and see what exactly is the 2 degree polynomial which they get back. And in this case they will be getting back this polynomial and they might end up taking 3 as the function output. So, as you can see here that the error correction completely fails here. Parties have absolutely no idea which share to ignore and what are the remaining 3 shares they should consider for reconstructing the function output. Depending upon which 3 shares they take, they will be getting different possible outputs, and as a result they will be completely clueless which output to consider as the right output. So, that is precisely the problem number 1 associated while maintaining the BGW invariant. Namely, if we let the parties simply multiply their respective shares of the multiplication gate inputs, then that will cause a problem, because the number of shares that we require now to reconstruct a function output after error correcting t errors is less, okay, because the degree of the sharing for the gate output is now no longer t, it is now a 2t degree polynomial. Okay. So, that is the first problem associated here. Now, the second problem is a more serious problem, then this is related to the privacy here. So, for the moment imagine that we are working in a setting where t is less than n over 4, we are taking still the same function, namely a function where we will have just one multiplication gate, and now our proposed protocol should work. There should not be any error in the correctness property, because we are now assuming that we have t less than n over 4. So, even if up to t incorrect shares are provided for the value y, we have sufficient redundancy. The Reed-Solomon error correction algorithm has sufficient redundancy to error correct those t errors and correctly recover back the 2t degree polynomial through which the value y is secret shared. However, the problem now is that this polynomial c of z, this c polynomial in the z variable, which is a 2t degree variable, this c polynomial which is a 2t degree polynomial is no longer a random polynomial. Okay. So, it is not the case that all the coefficients of the c polynomial except of course, the constant term are random coefficients. Okay. Whereas, the BGW invariant requires that if the gate inputs are secret shared, then for maintaining the privacy we require the output of the gate to be secret shared through a random t degree polynomial, but that is not happening here, because this c polynomial is no longer a random polynomial, its coefficients are not random. For instance, this c polynomial does not constitute an irreducible polynomial, because its factors are the a polynomial and the b polynomial. Whereas, if c is a random 2t degree polynomial, then with equal probability it could have been a reducible polynomial, and with equal probability it could have been an irreducible polynomial. But as per the proposed protocol, we are landing up in a case where the c polynomial is always going to be an irreducible polynomial, and hence it is not a random 2t degree polynomial. Consequently, in the proposed protocol, if we let the parties simply learn the function output y by asking the parties to make their shares of y, namely the shares lying on the c polynomial public, then it may end up leaking information about the inputs of the parties, and which simply goes against the privacy property. So, again let me demonstrate this problem with an example here. So, my field for demonstration purpose remains the same. My evaluation points associated with the parties are 1, 2, 3 and 4, and here 1 out of the 4 parties could be corrupt. Imagine that the input of the first party is 1, which is VSS shared through the sum is sharing polynomial 1 plus 2z, resulting in the shares 3, 0, 2 and 4 for the first, second, third and fourth party respectively. Imagine that the second input is 4, which is VSS shared through the sum is sharing polynomial 4 plus 0z, resulting in the shares 4, resulting in the share 4 for all the 4 parties. And suppose the parties locally multiply their shares of x1 and x2, and imagine for simplicity here that there is no malicious corruption here, everyone behaves honestly, in the sense that even the corrupt party makes public the right share of y. Okay. So, every party is making here public the right share of y, you can see here, and now by interpolating the shares here, interpolating the shares of y which have been made public, the parties will reconstruct a 2 degree polynomial 4 plus 3z. You might be wondering, it is not a 2 degree polynomial. Well, it is a 2 degree polynomial where the coefficient of z square is 0, and then they will take 4 as the function output. So, now imagine P 3 is corrupt, the third party is corrupt, but it is corrupt in a passive way, it is not maliciously corrupt. So, you can see here that the party P 3 is under the control of the adversary, but it has made public the right share. So, that is why in this example there are no incorrect shares for the value y at the time of reconstructing y, due to which we are able to reconstruct the function output. So, you might be wondering that this protocol is maintaining the privacy property, but I am going to show that that is not the case. Now, since P 3 is corrupt, what exactly it learns? It learns the function output, and it learns all the shares of y which are made public by the individual parties, and hence the corresponding 2 degree sharing polynomial through which the value y has been secret shared, namely the C polynomial, and all the values which are question mark here are the unknown values from the viewpoint of the party P 3. Now, party 3 also knows that since the function output is 4, the possible input scenarios are the following: either the first input is 1 and the second input is 4, or the first input was 2 and the second input was also 2, or the first input was 4 and the second input was 1, or the first input was 3 and the second input was 3. There is no other possibility because the inputs can take any value from the set 0 to 4. Okay. So, for instance, x 1 can't be 4 and x 2 can't be 4, because x 1 being 4 and x 2 being 4 should result in an output 1, but the output that parties learn is here in this case is 4. Now, what we are going to show here is that there are certain possibilities for x 1 and x 2 which the corrupt P 3 can rule out based on the values which it has learnt in this execution, and this simply implies a violation of the perfect privacy, because if the proposed protocol for evaluating the multiplication gate is perfectly secure, then the view of the corrupt P 3, namely whatever values the corrupt P 3 learns in the protocol which are marked or which are shown here in bold, it should not lead the corrupt P 3 to conclude what could be the possible x 1 x 2 and what could not be the possible x 1 x 2. Okay. So, for instance, suppose the corrupt P 3 makes the hypothesis that is it possible that P1's input was 2. It makes this hypothesis. Now, in order that P1's input is 2 and the share which the third party has received corresponding to that input is 2, it must be the case that party 1 has secret shared its input using the summation sharing polynomial 2 plus 0z. That was not actually the case. Actually, P1 has secret shared the input 1 using the sharing polynomial 1 plus 2z. But right now what we are doing is we are just doing some hypothesis on the behalf of the corrupt P 3. The corrupt P 3 is thinking in its mind, is it possible that P 1 has participated in the protocol with x 1 equal to 2, and the answer is yes. P 1, it is quite possible 2 and 2 to the first, second and fourth party respectively. And now since the input x 1 has been fixed to 2, that means adversary is basically checking this particular combination. So, since x 1 has been fixed to 2, x 2 should also be 2. Now, it is quite possible that x 2 was 2, namely the input of the second party was 2 and the second party has given 4 as the share to the third party, provided his sharing polynomial was 2 plus 4z, in which case P1 in which case P2 should have distributed the shares 1, 0 and 3 to the first, second and fourth party respectively. And now you can see magically what is happening here is that if P1's share would have been 2 and 1 for x1 and x2, then it would have made public the share 2. If P2's share would have been 2 and 0 for x1 and x2, then it would have made the share 0 for y public, and if P4's shares are 2 and 3, then it would have made public the share y, the share 1 for the value y, and all these shares would have led to the interpolation of the C polynomial 4 plus 3z. So, that means adversary cannot rule out the possibility of x1 being 2 and x2 being 2, namely based on the values which a corrupt P3 has seen in the protocol execution. So, it has seen the values in the protocol execution corresponding to 1 and 4, because that was the real inputs of P1 and P2. But what I have shown in this table is that the view of the corrupt P3 is also consistent with x1 being 2 and x2 being 2. Namely, it is quite possible that there is some randomness for P1 and P2 such that whatever the values P3 has seen in this execution, the same values P3 would have seen if P1 would have participated with input 2 and P2 would have participated with input 2. Right. So, that means two of the possibilities adversary cannot rule out. So, x1 being 4 and x2 being 4 is possible, and x1 being 2 and x2 being 2 is also possible. Now, adversary is trying to see whether it could be possible that x1 was 4 and x2 was 1, given that the bold values are the values which adversary has seen in the protocol execution. Now, if x1 was 4 and if P3's share was 2 and if P1's sharing polynomial was a 1 degree polynomial, then that could be possible only if the sharing polynomial of P1 was 4 plus z, leading to the shares 0, 1 and 3 for the first party, second party and fourth party respectively, and the second party's input being 1 with P3's share being 4 is possible only if P2 has used the 1 degree polynomial 1 plus z for secret sharing as input. But now you can see that if these are the shares of x1 and x2, then that will not lead to the shares of y being 2, 0, 3 and 1, because if P1's shares for x1 was 0 and for x2 was 2, then P1 should have made the share 0 public for the value y. P2 should have made 3 public as its share of y, and P4 should have made public 0 as the share for y, but they have made public the shares 2, 3 and 1 respectively. So, that means now adversary can rule out this possibility. That means based on the values which are tick marked here, which it has actually seen in the protocol, it can say that no, it is not the case that I have participated in the protocol where P1's input was 4 and P2's input was 1. And in the same way, now let us check the fourth possibility, whether x1 being 3 and x2 being 3 is possible. Well, in that case the P1's sharing polynomial should have been 3 plus 3z and P2's sharing polynomial should have been 3 plus 2z, and again in that case it turns out that adversary can rule out the possibility of the first and the second input being 3, because that is not going to be consistent with the shares of y which the corrupt party sees in the protocol while reconstructing the function output. So, that means there are two possible input scenarios which the adversary can rule out here, and that is a violation of the privacy condition. And this second problem is arising here because this C polynomial, it is not a random 2 degree polynomial. It is, for instance, a reducible polynomial whose factors are the A polynomial and the B polynomial. So, with that I end this lecture. To summarize, we have seen here the challenges associated while evaluating a multiplication gate for maintaining the BGW gate invariant. In the next lecture, we will see what exactly we have to do to deal with the challenge, and these are the references which are used for today's lecture. So, in the first course, secure computation part 1, we have a lot of discussion regarding the challenges associated while evaluating the multiplication gate. So, most of my explanation in today's lecture is taken from that course. Thank you.